This lesson covers all of Chapter 10, or at least the parts of Chapter 10 that I mostly want to talk about. We'll kind of come in and fill in the blanks of Chapter 10 a little bit later, but today is mostly an overview of Chapter 10. Chapter 10 deals with free radical chemistry, and radical carbons are very similar to carbocations. So when we look at these four compounds right here, what you should notice is that these two compounds are radicals. That's what that little point means right there. That means that the carbon is making three bonds. So it's making a bond to a methyl group here, here, and here. And then the fourth bond is missing and is replaced by a single lone electron. This means that this carbon has access to 7 total electrons and does not have an octet. And that's what makes it like a carbocation. If you look at this methyl carbocation right here, it only has access to 6 total electrons, and then it has an empty p orbital, an empty unhybridized p orbital. So this methyl cation only has 6 electrons. The methyl radical has those same 6 electrons that the methyl cation has, plus a half-filled p orbital. So in terms of stability, it would be better to have 7 electrons than to have 6, and better to have 8 total, but if you can't have 8, then 7 is better than 6. So the carbocations will always be less stable than a similar carbon radical. And in fact, the carbocations are going to be less stable than all of the carbon radicals that we're going to deal with. So carbocations are kind of a unique case. Carbon radicals are slightly more stable as a general rule, but they do keep the same hybridization of their original carbocation kind of ancestor. Think about giving a carbocation a single electron, and that's how you stabilize it a little bit by turning it into a radical, but it keeps the hybridization, still sp2 hybridized. So in these 4 examples right here, this carbon is sp2, this carbon is sp2, that carbon, which is a radical carbon, is sp2 and sp2. In terms of stability, the carbocation is the least stable, and then based on the similarity to carbocations, we expect a more highly substituted carbon radical to become progressively more stable. So this, of the carbon radicals, this would be the least stable carbon radical. This would be the most stable because it's a tertiary carbon radical. And this right here would be a secondary carbon radical. Secondary carbocations have a tendency to undergo shifts, as do secondary carbon radicals. And in fact, primary carbon radicals do form, and they have a tendency to shift, but we don't expect that shift to occur. So if this had been a carbocation right here, we would expect the hydride to move over in kind of an unstoppable step of the mechanism, and your carbocation would shift. We would expect that to represent the major product pathway. With radicals, we know that they can shift, but we don't expect them to unless the product requires them to. So if I give you the starting material and the product, and it was obvious that a shift occurred and there was a radical, then you say, well, okay, we'll shift the radical. But for the most part, radicals kind of tend to stay where they are, and that's what we expect them to do. Generally speaking, alkanes are pretty useless. From an organic chemist perspective, at least. From a home heating perspective, they're quite useful. Alkanes are the primary component of natural gas, such as, it's mostly methane. There's a little bit of ethane in there, and probably some larger alkanes. But for the most part, it's methane, and we burn it. Liquid propane is compressed and put in cylinders and used as a heat source. Backyard barbecues or backyard grills are typically propane powered. But chemically speaking, you're just burning it, and you're going to make carbon dioxide and water, which you don't want chemically, and all you really want out of that is heat. That's what you're burning it for. Well, free radical halogenation of an alkane gives us a new way of taking alkanes and converting them into alkyl halides. And once you have the alkyl halide, then you can use your advanced knowledge of all alkyl halide chemistry from one of the tables that we've looked at to do all kinds of chemical reactions. The reagents that we use in free radical halogenation of an alkane are a molecular halogen, not a halogenic acid. So HX, which is HCl or HBr, have little to no effect on alkanes at all. And so we use a molecular halogen, typically Cl2 or Br2, and we have to heat this reaction up, that's what the delta symbol means, or add in UV light. And these are two equivalent ways of trying to denote that we're adding in UV light to the system. This is a net endothermic process for at least the bromine it is, and for the chlorine it's pretty tough, kind of thermodynamically speaking, to get the reaction to run, so we continue to add in the sources of energy in order to produce our product. A secondary product of this reaction is going to be a halogenic acid, and this will build up over time, probably in the gas phase, and bubble out of the reaction container if it's solvated. And that hydrogen comes from this center carbon right there. The methylene carbon originally had two hydrogens. You'll notice in our product that one of those hydrogens had to leave in order to make room for the halogen to add in. And then the X2, one of the halogens, ends up on the alkane to become an alkyl halide. Another one comes off as a halogenic acid. This is an inorganic product, and so don't really care about it that much. These free radical reactions are typically characterized by 4 distinct phases of the chemistry. The first step in a free radical mechanism is typically the initiation step. I'm going to try to use a consistent color scheme, so the initiation step will continue to be this magenta color. And this initiation step is strictly inorganic, meaning that my molecular halogen is being split apart into 2 halogenic radicals. This is why we have to add in the UV or the heat. It causes these halogens, which represent the weakest bond in the system, to break apart and form these radicals. You don't have to show this step when you're showing the mechanism unless I specifically ask for it, because the rule of thumb is if it doesn't involve carbon, then we just kind of jump past that step when we're trying to draw out the mechanism. So I can kind of skip this initiation step unless I ask for it. Or you can skip the initiation step unless I ask for it. You should know it's happening, but you can generally kind of gloss over it. So you would actually pick up this mechanism from the formation of the halogen radical. And this second step is the carbon radical formation step, the CRF, and I will continually color this in black. In the carbon radical formation step, you're typically an inorganic precursor radical, which we made in the initiation step, is going to react and rip a hydrogen off. Hopefully you noticed a unique feature of these arrows that I'm showing. These are what are referred to as half-headed arrows. A full-headed arrow denotes the movement of an electron pair. A half-headed arrow is showing an electron moving without its pair by itself. So these 2 curved arrows right here that I didn't mean for this to look like a S or a reverse S. But what I'm trying to show here is that in this bond containing 2 electrons, one of them, denoted by the half-headed arrow, hops onto the halogen and the other one hops onto the other halogen. This is referred to as a bond cleavage. So the lytic, we're going to use the term lytic, that refers to breaking something, and it's a homolytic bond cleavage. Homo meaning 2 of the same. So we have 2 of the same types of atoms are undergoing a bond cleavage, and each of them end up picking up an electron. In this carbon radical formation step, then we see the typical 3 half-headed arrows. And in the mechanisms today, you're going to see that 3 half-headed arrow thing over and over again. When the carbon radical is formed, the carbon radical is going to form on the more stable position. A secondary carbon radical is more stable than a primary carbon radical for the same reasons that a secondary carbocation would be more stable than a primary carbocation, namely induction and, most importantly, hyperconjugation. So after the initiation step and the carbon radical formation step, the next step is referred to as a propagation step. These free radical reactions propagate themselves, and what that means is that by the time you finish a free radical reaction, you should regenerate the initial radical that started the chemistry in the first place. So again, I have 3 half-headed arrows. These 3 half-headed arrows are going to tear apart a molecule of whatever halogen I'm using in this reaction, and that will form my final organic product. This is what I'm looking for. And I'm also going to make this inorganic product, which has to be the same radical that started the chemistry in the first place. So initiation makes the first radical, then you have a carbon radical formation step, which kind of moves the radical from the inorganic to the organic the carbon, and then the propagation step where the carbon radical grabs a halogen to make the major organic product that the question is asking us to make, and then also to reproduce the initial radical that started the chemistry in the first place. These are the three steps that we expect to see in free radical chemistry. Nothing can last forever, so when you start a free radical reaction like this, if you'll notice, if everybody does exactly what they're supposed to do, then you only ever needed one UV light photon to make this happen. That photon provides the energy for the homolytic bond cleavage. It makes your halogen radical, and then that halogen radical will reproduce another halogen radical, and you'll never run out of halogen radicals. And so in actuality, in the laboratory, you have to continue to put UV light into the system, and one of the reasons for that is what's called a termination step. So this is a low probability event, and we do not show this in our mechanism unless we specifically ask, how could this reaction terminate? And termination involves two half-headed arrows, and it involves two radicals coming together in solution. Radicals form in such trivially low concentrations that the probability of two radicals finding each other in solution is very, very low. It is worse. Imagine that you have one soulmate in the entire global population of 7 billion people, and your job is to find that one person. That is a higher probability scenario than the probability of two radicals finding each other inside of a solution where there are often trillions of molecules, and there's just a handful of these radicals. So this is a very low probability event. But the way you make something a certainty is you take a low probability event and multiply it by time. So as time progresses, and on a molecular scale, minutes is a tremendous amount of time. So over the course of minutes, you will eventually start to see these radicals find each other. They kind of kill the reaction because they use up two equivalents of radical, and you do end up with your product, the one you want, but it doesn't propagate the reaction the way you want it to. So termination is not a step that we typically show, but it definitely happens to some extent. There is also another possible termination product, and just if we're going to talk about low probability occurrences, which is what we would say would happen for two radicals to find each other, then we should consider other low probability occurrences, and this would be two carbon radicals bumping into each other to form this dimer right here. And this really didn't accomplish anything useful. We did manage to make our carbon chain bigger, but it's still not an alkyl halide. It's still an alkane, and we probably just need to burn it at this point, which is the typical fate of most alkanes from a human perspective. What other possible products could we get out of this reaction besides a dimerized alkane? Well, radicals can form on primary, secondary, and tertiary positions of a carbon. And so here I showed you the major product where we would expect a secondary carbon radical to dominate, but you could have that same initiation step, only this time instead of the halogen radical bumping into the secondary hydrogen, it could bump into the primary hydrogen. And if it bumped into the primary hydrogen, you could form a primary radical, which can occur. It's not as forbidden as a primary carbocation. And then we have a propagation step, so now we would produce a 1 halo propane as opposed to a 2 halo propane. When we think about, well, which halogen should we use, this is a similar question that we saw before, and it requires us to remember the reactivity trend of the molecular halogens. Fluorine, F2, is the most reactive of the molecular halogens, and not to be confused with the trend of the acids. So hydrofluoric acid is the least reactive acid, but this question is not asking you about the reactivity of the acid, it's asking you about the reactivity of the molecule. And CO2 is more reactive than Br2, which means that the Cl2 would be less selective. When you have a chlorine radical right here and it bumps into things, it is not going to wait to find the best available thermodynamic situation. It's just going to rip a hydrogen off. And so what that means is if you have a chlorine on here, then you still expect for this secondary to be your major product, but instead of having, let's say, 80% of this and 20% of this, with bromine, which is less reactive and more selective, the chlorine would give you something closer to 60% and 40%. I believe your book actually walks you through the math of that particular scenario, and I'm going to skip that math for the time being. It usually doesn't fit into the context of the semester. There's other things I'd like to show you besides that. The point of this question is chlorine, molecular chlorine, is more reactive and therefore less selective. So the ratio would be smaller. You would expect to get a 6 to 4 ratio, which ends up being 3 to 2, as opposed to with bromine, I think it's closer to like a 9 to 1 ratio. So it's a very high ratio of secondary to primary when you have bromines on there. If you look at the question that I asked in the lesson right here, I asked you to show for the monohalogenation of propane. And that's true. You actually have to control this reaction in the laboratory and only allow it to react long enough to produce a single halogenation event. Because if you let it sit in there and just cook inside of your reaction container, this product that we got of monohalogenation will start to react a second time with your radical, and you'll undergo what's referred to as polyhalogenation. So polyhalogenation is an event that will start to occur the longer you let this reaction run. And I think the question asks, how would you change the reaction conditions to produce a polyhalogenated product? And the answer is you just let it cook longer, and polyhalogenation will eventually become inevitable. Here I have kind of stripped down the mechanism. Remember I said earlier that this initiation step is inorganic, and therefore you can jump right into the carbon radical formation step. So this is actually kind of the laziest possible correct mechanism for the free radical halogenation of an alkane. The next example is kind of a nice follow-up to the previous chapter where we looked at electrophilic addition. In its standard electrophilic addition reaction of an alkene with a halogenic acid, we expect for the alkene to reach out into the hydrogen, bump off the halogen, we end up with a carbocation, then the halogen comes back and captures the carbocation. Hopefully that mechanism is one that you're familiar with. Chemists started running this reaction, and after a while what they realized was with hydrobromic acid and only hydrobromic acid, not hydrochloric acid, what they found was that you would actually get a mixture of these two products. This was generally the major product, the one that we would expect, the Markovnikov addition of a bromine to this alkene, but they also got some of this anti-Markovnikov bromination occurring. And it wasn't a lot, but it was enough that it seemed unlikely that the carbocation mechanism was accounting for this product. You will get some primary carbocation. Given trillions of molecules in a solution, a few of them will be so poorly behaved that they will form a primary carbocation. But when they were running this reaction in the laboratory, they were finding that they were getting a lot more of this mono-bromo-propane than you can explain by thinking of a primary carbocation. And so one of the things that eventually they realized was molecular oxygen, the O2 that we breathe, is a free radical initiator. And so they thought, well, if a little bit of O2 causes us to form a little bit of this, what happens if we flood the system with O2? Well, O2 is it's hard to flood a system with O2. You can actually put liquid oxygen inside of a reaction container, but then it becomes explosively flammable. So instead they use these peroxides. Right? And you can run this reaction in the light to generate the radical, but it's more common in your textbook, and I've not run these reactions in the laboratory, so I can't speak based on laboratory experience. But your textbook tends to show this as a peroxide, this RAR right here. This is a standard peroxide, and it has the initiation step. Now, this anti-Markovnikov bromination of an alkene, is this reaction we're looking at right here, has two initiation steps. Both of them are fundamentally inorganic, or at least not related to the organic chemistry of the alkene. So unless I tell you otherwise, you can just jump right to the bromine radical. But let's pause for a minute to figure out what's going on. This peroxy radical initiator is a very weak bond and breaks easily. With a light tap of a UV photon, it will pop, and we end up with this peroxy radical right here. Well, this is just an oxy radical because The second oxygen is gone, so we don't use the peroxy term anymore. This oxy radical in a 3 half-headed arrow mechanism will pull apart hydrobromic acid to produce a more stable alcohol and a bromine radical. It is the bromine radical that's now involved in the carbon radical formation step. Just like we saw in the previous halogenation of alkanes, once you get to the halogenic radical, then you bring in your organic compound and it pulls apart this pi bond. These same 3 half-headed arrows that we see tell the story of one radical electron from the bromine offering up kind of a handshake. The pi bond breaks. One of the electrons from the pi bond goes out to meet that radical to form the sigma bond between the carbon and the bromine, and the other electron in that pi bond is now kind of a loner. It gets cut free, and it will force the bromine over to the less substituted position so that the radical will be at the more substituted position. So in this carbon radical formation step, that's when the bromine is pushed to the anti-Markovnikov position. The final step is the propagation step, and in the propagation step we need to get rid of this carbon radical and put something on there that's not a radical, and at the same time get our bromine radical back. And so hydrobromic acid, which we intentionally added to the solution, is all over the place, and we see another 3 half-headed arrow mechanism where this radical bumps into the hydrobromic acid, pulls off a hydrogen, and reproduces your bromine radical. This bromine radical right here is essentially been reinitiated and can go back and start a second round of chemistry. How do you avoid this anti-Markovnikov product in the laboratory? So what if we don't want this one right here, and instead, let's go back quite a ways. And what if this is the only product we want? Well, it was oxygen that was making a little bit of this, and peroxides that were making a lot of it. So, well, don't add peroxides. And that's the obvious answer of how to only get the Markovnikov product. And then the second answer is don't add oxygen. Well, since oxygen is 20% of the air that you breathe, you really can't just evacuate all the oxygen in your laboratory. So a lot of times what chemists will have is a glove box, and it is a pressurized, kind of an airtight box. It's usually made out of plexiglass, and it has these large gloves that are kind of glued onto the box, so you can stick your hand inside the gloves and then work with your hands inside of the box in the gloves on the chemistry while nitrogen gas is piped into the box. And so this is how we produce, they call this a glove box, and it's usually an oxygen-free environment. The other way to do it is they will not worry so much about the oxygen, but they'll run it in the dark. Because if you have molecular oxygen present, then this initiation step, even with molecular oxygen, kind of prefers the presence of UV light. And so if you just turn off all the light together, then that can kind of slow down the radical chemistry. So a glove box is the best answer to this question. How do you avoid the anti-Markovnikov product? You would use a glove box. And the second best answer is turn off the lights. And that's kind of a stupid answer because you can't work in a laboratory without some light source. And you might ask, well, normal room lights aren't supposed to give you UV radiation. They're supposed to give you visible light. And the answer is they give some of both. And in fact, in the laboratory, there is a reaction that we have the students of first semester organic chemistry run where we need to irradiate a pi bond in order to split it homolytically. We pop the pi bond to make a diradical. And we do it with just a normal work light, just one you would buy at the hardware store that has a halogen light bulb in there. And even though it's primarily meant to be a visible light source, and it gets very hot, which tells you that it's also a pretty significant infrared light source, there's enough UV light coming off of a typical light bulb to be enough. In fact, there's enough UV light coming through a window. Unless you have, I guess, a UV filter on your window, a normal old-fashioned window, that you would expect for that to be sufficient to generate some of this anti-Markovnikov product. So you want to kind of prevent incident light from striking your reaction flask, and you would want to avoid the presence of oxygen. That's how you would get the highest yield of not this product, but the regular Markovnikov product. What if we tried all this chemistry with hydrochloric acid? You know, we added in the peroxy initiator, and we also had the UV light present. What would happen? Well, not much. You'd pretty much just get your Markovnikov product. You get the exact same products, even if you hadn't added in the peroxy radical initiator. And so you would just waste reagents in this and go to a lot of trouble for nothing. The point of this question right here, of what would happen if you tried to do this with hydrochloric acid, the answer being you would not get a radical, is exactly that. Hydrochloric acid does not go through this same radical pathway that the hydrobromic acid does, and it's a thermodynamic issue. And so it's just not favored when you put hydrochloric acid in here. So this is kind of the first time that a chemical reaction is extraordinarily unique to just one of your halogens. And the bromine here does the anti-Markovnikov free radical chemistry much better than the hydrochloric acid will. The third reaction we want to look at here is an industrially very important reaction, and this is free radical polymerization. And this is the chemical reaction that began the modern age of plastics, and which is, I spent a lot of time on environmental chemistry. The modern age of plastics is not a good thing from my perspective as an environmental chemist. When I think of all the environmental contamination of plastic that is now in the rain, in the snow, and in the air you breathe. We have plastics everywhere. This is vinyl chloride right here. And you can polymerize vinyl chloride to make polyvinyl chloride by using a free radical initiator, and usually you have to turn up both the pressure and the heat substantially. A typical organic chemist is interested in making the reaction work on a small scale under controlled conditions at low pressure in a laboratory. Chemical engineers want to make things big, and a lot of times that involves very high pressure, very high temperature, and massive reaction containers. Think 10,000 liter reaction tanks that are double reinforced steel walls that they can pump 100 ATMs of pressure into. So a chemical engineer really kind of took this basic understanding of organic chemistry and applied it writ large to the synthesis of polyvinyl chloride, which is where we get PVC pipes from, which is kind of defines our modern plumbing. So this reaction here has a lot of industrial utility. And what this is trying to show in brackets is that it just continues on indefinitely in both directions. So I have taken this vinyl chloride and explicitly only shown the formation of what's called a tetramer, meaning that I've taken my monomer and combined 4 of them together to get the tetramer. But these dashed lines and brackets suggest that it's going on and on and on and on and on. And in reality, PVC is probably made of these polyvinyl polymers that are millions or even trillions, or probably, I have no idea, but it's a tremendous number beyond the typical scale of human counting, that you start ending up with these individual strands, and then you pack them together in an industrial fashion. They're held together by strong dispersive force interactions as well as covalent cross-linking to give you the structural integrity of a typical PVC pipe. So mechanistically, what happens here? As a chemist, well, we have an initiation step. And so this is that peroxy radical initiator. As an example of what a typical peroxy radical initiator might look like, this is one called benzoyl peroxide. And you might actually have experienced benzoyl peroxide at some point in your life. Hopefully not anymore, but probably some of you. It is an anti-acne agent. Benzoyl peroxide, and I didn't notice this until I was walking down the aisle of the pharmacy, and out of the corner of my eye I saw benzoyl peroxide on a bottle as I was walking past, and so I circled back and found it was an anti-acne medication. Topically, you can put this compound on your skin in the presence of the UV light that is found in typical sunlight, or even under the fluorescent lights that I'm currently sitting. That's going to pop this bond, and you'll end up with that free radical. This free radical is toxic to living cells. Your skin is mostly dead, and you've got a lot of cells that you can lose before it starts to create problems. It's the single-celled organisms that are causing the inflammation associated with acne that are dying in mass in the presence of this free radical, as this radical electron kind of tears into the structural integrity of the biomolecules. I did change, for the sake of fitting all this on a single PowerPoint slide, I did use a common abbreviation for a benzene ring. When a benzene ring, which is what this is a substituent coming off of a molecule, we gave it a different name to be as confusing as possible. It's called a phenyl ring, P-H-E-N-Y-L, and the common abbreviation is capital P, lowercase h. not to be confused with lowercase p, capital H, which we use to denote the acidity or alkalinity of a solution. So this pH refers to the phenyl ring right there. It's just an abbreviation, and we'll deal with this later. All of this was a tangent. The purpose was to give you perhaps kind of a hands-on example of what ROOR actually means when you see it on a slide or on a mechanism. All right, so that was a long preamble. Here's my initiation step, and then my propagation step, sorry, not propagation, the carbon radical formation step, is where that initial radical will now dig into the pi bond. One of the electrons from the pi bond reaches out to meet it in our standard 3 half-headed arrow mechanism, and the other radical ends up here on this carbon. Then the propagation step is actually a continuation of the carbon radical formation step. So in this particular example, it's a little bit confusing. It's not quite clear where the carbon radical formation step ends and where the propagation step starts, because the propagation step is actually generating another carbon radical. This radical electron bumps into the pi bond, pulls this thing apart, and joins the two carbons together while reinitiating a carbon radical. So a little different than we've seen before. We're not actually remaking our original inorganic radical. We're actually making a carbon radical. And then this just keeps going. So we just have more of these carbon radical formation / propagation steps. This right here would be the trimer. This was the dimer. If I were to go through one more round of this, I would end up with this tetramer that I showed up above. But the truth is, this process just continues for a very, very long time. And when I first saw this reaction, I thought, well, how on earth do they get rid of this RO? This is either an ether or an ester, and you probably don't want that on your PVC pipes. And the answer is, nobody, doesn't matter. Like, I don't think anybody cares. This RO group right here represents, as this thing starts to polymerize, and you get trillions or quadrillions of these monomeric units that are all joined up on this PVC, at some point, the percentage of the molecule that this actually represents is such a vanishingly small percentage that you can just leave them on there and it won't affect the structural integrity of your PVC pipe. PVC pipes are made often just to build stuff or to put tubing in under high strength. So it's not like you have to have a chemically pure PVC pipe. Nobody cares about the purity of your PVC pipe. And I'm also, as a tangent, when I think about the show Breaking Bad, I really wonder how often people care about the purity of chemicals, the way that chemists tend to care about the purity of chemicals. A termination event will eventually occur. You can imagine two of these growing chains of PVC polymers might actually bump into each other, or another termination event that I did not show was that one of these peroxy radicals could bump into the growing end of your PVC polymer right here, and that could cause it to cap off prematurely. And so we end up with kind of a bell curve distribution of chain lengths, where the majority of them are going to be very, very, very long, but you will see some that are very small. It just kind of depends on how quickly they terminate. When you make, going back, let's go back to this slide, just so you can appreciate the animation effect right here. Notice the aster C showing up there. That is to remind me, to tell you, that we actually ended up making chiral centers in this compound. Okay? So when this polymerization event occurs, it is common for this to end up being a chiral center. And since our starting material wasn't chiral, and our reagent is not chiral, that means that these chiral centers are made completely randomly. Or in a word choice that I will explain why I'm going to say in a minute, they are made without a strategy. Okay? These are going to be R and S randomly down the line. And when you think about millions upon millions or trillions upon trillions of these individual chiral centers all doing whatever they wanted in the moment of the chemical reaction, you end up with kind of a stereochemical mess. And the original plastics that they synthesized, not PVC, but imagine that this was just a regular alkyl group, you could make a plastic out of that. And the plastics that they made that were not stereochemically controlled, that just had random stereocenters, did not pack as well as they could have, and so the plastics tended to have weak intermolecular forces of attraction between them. This means that they were soft and kind of pliable, and they melted, and they weren't very structurally sound. And think of if you ever went to Chuck E. Cheese and spent $5 earning tickets, and then took those tickets to the counter to redeem the 25-cent toys that they had, or the 1-penny toys. They were all that super cheap plastic. And when they first started synthesizing plastics, that was a big problem, that the plastics came out and they just weren't strong enough because they were too stereo irregular. So what they needed to come up with were some stereo regular polymers. And so the process that I just described to you, where all of these chlorines right here show up randomly, is referred to as atactic. A means without, and tactic means strategy. So that's why I used the term without a strategy originally. Think of this red group down here as the chiral center that you care about, and sometimes it's down. We'll call this R. I don't know what the priorities are, but maybe this is R and this is S, and then a couple R's and then some S's, and it's just random the whole way down the string. This is not a very structurally sound plastic polymer. So what they need to is come up with things that are either the same chiral center every time, and those are referred to as isotactic, meaning the same strategy, or syndiotactic is an alternating strategy where it's every other one changes. And so the conversion from the original atactic polymers to these stereoregular polymers, whether they're isotactic or syndiotactic, was eventually discovered by two Italian scientists with the last names of spelled like that. I'm going to mispronounce them, but it's Ziegler and Nada is how I would butcher those names in English. The Ziegler-Nada catalysts represent a family of different catalysts, and they approach the stereochemistry problem the same way that biology does. Biology takes an achiral starting material and then couples it with a chiral catalyst, and the chiral catalyst is what makes the product chiral. Ziegler and Nada use that same strategy to come up with a variety of different chiral metal catalysts, and they catalyze the polymerization to produce syndiotactic or isotactic, and they actually have an entire family of catalysts that kind of allow you to fine-tune exactly the chirality of your polymer as it grows, depending on what the groups are. And so if you wanted a stereoregular PVC pipe and you needed that plastic synthesized in a stereoregular way, then you would have to choose the appropriate Ziegler-Nada catalyst. And that's an ongoing field of research. There are people that are still adding to the wealth of various Ziegler-Nada catalysts that are available.